Look up at the night sky, and what do you see? A scattering of stars, perhaps a distant planet or two, all seemingly silent and unchanging. But what if I told you that every flicker of light, every subtle shift in motion, is part of an ancient, ongoing conversation, one that spans billions of years and countless galaxies? The universe is far from silent. It's alive with a hidden language, a cosmic dialogue written in the very fabric of space itself. This isn't just poetry, it's science. And today, we're going to decode it. Think about the last time you watched a sunset, the way the light changes, bending through the atmosphere, painting the sky in hues of gold and crimson. That light isn't just beautiful, it's carrying information. It's telling a story about the sun's composition, its temperature, even its age. Now, stretch that idea across the cosmos. Every star, every galaxy, every swirling nebula is doing the same thing, broadcasting its secrets in a language of light and motion. Some of these signals take millions, even billions, of years to reach us. When we look up, we're not just seeing stars, we're reading messages from the distant past, whispers from the dawn of time itself. But light is only part of the story. There's another force at work, one so subtle we can't see it directly, yet so powerful it shapes the very structure of the universe: gravity. Imagine two stars locked in a silent dance, their movements choreographed by an invisible hand. Or a galaxy spinning gracefully, its outer stars moving faster than they should, hinting at the presence of something we can't see: dark matter. These gravitational conversations are just as rich, just as revealing as the ones written in light. Together, they form a grand cosmic narrative, one that scientists are only beginning to understand. And that's what we're diving into today: the hidden language of galaxies, the way space communicates, and why unlocking these celestial secrets doesn't just teach us about the universe, it teaches us about ourselves. Because every time we decipher another piece of this cosmic code, we're reminded that we're not just observers of the universe, we're part of the conversation. Light is the universe's oldest messenger, carrying secrets across the void in waves of energy we're only just learning to read. Picture a rainbow, not just as a splash of color, but as a barcode. Each hue represents a different wavelength, a unique piece of data. Now, stretch that rainbow far beyond what our eyes can see. Beyond the red, there's infrared, whispering tales of heat. Beyond the violet, ultraviolet screams with the energy of newborn stars. X-rays pierce through cosmic dust to reveal black holes feasting on matter, while radio waves hum with the echoes of galaxies colliding. This is the cosmic alphabet, written not in letters but in photons. When astronomers point a telescope at a star, they're not just capturing its glow, they're unraveling its DNA. Spectroscopy, the art of splitting light into its component wavelengths, lets us read the fine print of the cosmos. A star's spectrum is like its fingerprint, with dark lines where specific elements, hydrogen, helium, even traces of iron, have absorbed light. These lines tell us what the star is made of, how hot it burns, even how fast it's moving toward or away from us. It's how we know the sun is mostly hydrogen, or that distant quasars are racing apart from us at nearly the speed of light. But the real magic happens when light interacts with matter. Imagine a cloud of gas drifting between stars. When starlight passes through it, certain wavelengths get snatched up by atoms in the gas, leaving behind gaps in the spectrum, like missing teeth in a comb. These gaps reveal the cloud's composition, its density, even its temperature. It's how we've detected water vapor in the atmospheres of exoplanets, or found organic molecules in the depths of space. Light doesn't just travel, it transforms, carrying fingerprints of everything it touches. And then there's motion, the Doppler effect, the same phenomenon that makes a siren's pitch drop as it speeds past, also shifts starlight. When a galaxy races toward us, its light is squeezed into shorter, bluer wavelengths. When it flees, the light stretches red. This cosmic redshift is how Edwin Hubble discovered the universe is expanding, and it's still how we measure the acceleration of that expansion today. Every photon is a time capsule, a speedometer, and a chemist's ledger all in one. So the next time you gaze at the stars, remember, you're not just seeing points of light. You're witnessing a celestial telegraph, a billion-year-old conversation written in wavelengths. And with every spectrum we decode, we're learning to speak the universe's language, one photon at a time. If light is the universe's language, then redshift and blueshift are its accent-subtle changes in tone that reveal how fast and in what direction celestial objects are moving. Picture a train whistle racing past you. As it approaches, the sound pitches higher. As it speeds away, the pitch drops. Light behaves the same way. When a galaxy races toward us, its light waves get compressed, shifting toward the blue end of the spectrum. When it retreats, those waves stretch, turning redder. This isn't just a neat trick of physics, it's a cornerstone of modern astronomy, the key that unlocked one of the greatest mysteries of the cosmos. The universe isn't static. It's growing, and not just growing, but accelerating. Edwin Hubble made this groundbreaking discovery in the 1920s by observing distant galaxies. Almost all of them showed redshift, meaning they were hurtling away from us. But here's where it gets wild. The farther away a galaxy was, the faster it seemed to be receding. This wasn't just motion, it was evidence of space itself stretching, carrying galaxies along like raisins in an expanding loaf of bread. Hubble's observations shattered the idea of a steady, unchanging universe and revealed a cosmos in constant flux. Yet redshift isn't just about speed, it's a time machine. The light from a galaxy 10 billion light-years away isn't just telling us how fast it's moving now. It's showing us how fast it was moving 10 billion years ago. And when astronomers compared ancient redshifted light with newer observations, they found something astonishing. The universe's expansion isn't slowing down, as gravity alone would predict. It's speeding up. Something is pushing galaxies apart faster and faster, a force we've dubbed dark energy. This is where redshift gets really strange. If dark energy keeps stretching space, future astronomers might look up and see a sky nearly empty of galaxies, not because they've vanished, but because their light will have redshifted so far it's invisible to our instruments. The universe's own expansion could eventually erase its history, leaving only whispers of the cosmic dawn. But blueshift has its own mysteries. While most galaxies flee from us, a handful, like our neighbor Andromeda, are blueshifted, hurtling toward a collision course with the Milky Way. These rare exceptions remind us that while the universe expands, local dances of gravity still pull objects together in intricate, chaotic motions. Redshift and blueshift aren't just tools for measuring speed. They're clues to the universe's past, present, and future, a story written in light waiting to be read. Among the countless stars dotting the night sky, some don't just shine, they sing. Variable stars, the celestial metronomes of the cosmos, pulse with a rhythm so precise they've become one of astronomy's most powerful tools. Take Cepheid variables, for example. These stellar giants swell and shrink like a beating heart, growing brighter and dimmer in cycles that can last anywhere from days to months. But here's what makes them extraordinary. The speed of their pulse is directly tied to their true brightness. The longer the cycle, the more luminous the star. This simple yet profound relationship, first uncovered by Henrietta Leavitt in the early 1900s, became the yardstick that measured the universe. Before Leavitt's discovery, astronomers were like sailors without a compass, struggling to gauge distances beyond our cosmic neighborhood. But her observation of Cepheids in the Small Magellanic Cloud revealed something groundbreaking. By comparing a star's pulse rate to its apparent brightness from Earth, we could calculate how far away it was. Suddenly, the fog lifted. Edwin Hubble used this very method to prove that the so-called Andromeda Nebula wasn't just a nearby cloud of gas. It was an entire galaxy, millions of light years beyond our own. The Milky Way was no longer the center of creation, but one island among countless others in an ocean of stars. So why do these stars pulse in the first place? It's a delicate dance between gravity and radiation. Picture a Cepheid's outer layers as a balloon constantly inflating and deflating. When the star contracts, helium in its core gets squeezed, heating up until it ionizes, a process that traps radiation like a lid on a pot. Pressure builds until the outer layers erupt outward, only for gravity to pull them back in, restarting the cycle. This cosmic feedback loop creates the rhythmic flicker we observe, a heartbeat echoing across the light years. But Cepheids aren't the only cosmic timekeepers. Our Lyrae stars, smaller and faster, pulse in hours rather than days, helping map the ancient heart of our galaxy. Mera variables, red giants with moods as unpredictable as their namesake, flare and fade over months, offering clues to stellar evolution. Even our sun, seemingly steady, has subtle vibrations that reveal its inner workings. Each of these stars is a clock, a beacon, a storyteller, and by listening to their rhythms, we've pieced together the sprawling timeline of the universe. Yet mysteries remain. Some Cepheids flicker in ways that defy predictions, hinting at unseen forces or hidden companions. Others pulse in sync across vast distances, as if the cosmos itself is conducting a silent symphony. Every irregularity is a question, every anomaly a door to deeper understanding. Because when we measure the stars, we're not just charting space, we're tracing the very heartbeat of existence. Imagine turning on an old television set, tuning it to a dead channel, and hearing that familiar hiss of static. What if I told you that a tiny fraction of that noise isn't random, it's the faintest whisper from the birth of the universe itself? That's the cosmic microwave background, or CMB, the afterglow of the Big Bang, stretched and cooled over 13.8 billion years into a ghostly microwave hum that permeates every corner of space. It's not just background noise, it's a time capsule, a baby picture of the cosmos taken when it was just 380,000 years old. Back then, the universe was a scorching soup of particles, so dense and hot that light couldn't travel far before being absorbed. But as space expanded and cooled, electrons and protons finally combined into atoms, releasing light to travel freely for the first time. That ancient light, once blazingly bright, has been stretched by the universe's expansion into the microwave range, cooled to just 2.7 degrees above absolute zero. Yet embedded in that faint glow are secrets about how everything we know came to be. The CMB isn't perfectly uniform. If you could zoom in, you'd see tiny temperature variations, spots slightly warmer or cooler than their surroundings. These fluctuations, as small as 1 part in 100,000, might seem insignificant, but they're cosmic fingerprints. They trace the faint overdensities of matter in the infant universe, regions where gravity would eventually pull gas and dust into galaxies and galaxy clusters. It's like looking at a weather map of the early cosmos, where every hot and cold spot is a seed for the vast structures we see today. Scientists have mapped these fluctuations with stunning precision, using satellites like COBE, WMAP, and Planck. What they've found is astonishing. The patterns match predictions of cosmic inflation, a theory that the universe underwent a mind-boggling expansion in the first fraction of a second after the Big Bang. The CMB's subtle wrinkles are echoes of quantum fluctuations, microscopic ripples magnified to cosmic scales by inflation, then frozen into the fabric of space as matter and radiation decoupled. But the CMB isn't just a relic of the past. It's also a window into the universe's future. By studying its polarization, the way its light waves are oriented, researchers have found evidence for gravitational waves from inflation, clues about dark energy's role in cosmic acceleration, and even hints about the universe's ultimate fate. Some theories suggest the CMB might hold traces of other universes, a controversial idea that could rewrite our understanding of reality. And here's the wildest part: this ancient light is still interacting with us. When you stand outside on a clear night, a few photons from the CMB are hitting your skin, particles that have traveled uninterrupted since the universe was a newborn. They've witnessed the formation of stars, galaxies, even life itself, and now they're whispering their story to anyone who knows how to listen. The cosmic microwave background isn't just a snapshot of the past. It's a living message, a reminder that the universe is always speaking, if only we're patient enough to hear it. Einstein once described gravity not as a force, but as the bending of space-time itself, a cosmic fabric that could ripple like the surface of a pond. For decades, this idea remained just that, an elegant prediction buried in the equations of general relativity. But in 2015, humanity finally heard what those ripples sound like. The Laser Interferometer Gravitational Wave Observatory, or LIGO, captured the faintest echo of two black holes colliding over 1.3 billion years ago. That moment didn't just confirm Einstein's theory, it cracked open an entirely new window on the universe, one where we don't just observe the cosmos. We listen to it. Gravitational waves are unlike anything else in astronomy. Light can be blocked, scattered, or absorbed by dust and gas. But these ripples in space-time pass through everything: galaxies, nebulae, even the densest stars, utterly untouched. They're the universe's most faithful messengers, carrying secrets from events too violent, too hidden, or too ancient for traditional telescopes to see. When two neutron stars spiral into each other, or a black hole tears apart a star, the resulting tremors in space-time rush outward at the speed of light, undistorted for billions of years. And now we've built instruments sensitive enough to catch them. LIGO design is a masterpiece of precision. Two 4-kilometer-long arms sit at right angles with lasers bouncing between mirrors at their ends. When a gravitational wave passes, it stretches one arm while squeezing the other by less than 1,000th the width of a proton. That microscopic wobble shifts the laser light just enough to signal a detection. It's like measuring the distance to Alpha Centauri down to the width of a human hair. And what LIGO hears isn't just noise, it's a symphony. The chirp of merging black holes, the crescendo of neutron stars colliding, even the faint hum of the universe's background vibrations all tell stories no telescope could. But the real revolution began in 2017, when LIGO and its European counterpart, Virgo, spotted gravitational waves from a pair of neutron stars merging. For the first time, traditional telescopes saw the same event in gamma rays, X-rays, and visible light. This multi-messenger astronomy, combining gravitational waves with electromagnetic observations, was like suddenly seeing a movie with both picture and sound. The collision created a kilonova, an explosion so powerful it forged heavy elements like gold and platinum, scattering them across space. Without gravitational waves, we might never have known where to look. Now imagine what else we might hear. Supermassive black holes dancing at the centers of galaxies. the faint echoes of the Big Bang itself, even exotic objects like cosmic strings, theoretical defects in space-time left over from the universe's birth. Future detectors like the space-based LISA mission or next-generation ground observatories will tune into lower frequencies, catching whispers from events we can't yet conceive. Gravitational waves don't replace light-based astronomy, they complete it. Where telescopes show us the universe's face, gravitational waves let us feel its pulse. Together, they're revealing a cosmos far more dynamic, more violent, and more alive than we ever imagined. And every new ripple we detect is a reminder, the universe isn't just something we see. It's something we can finally hear. In the vast silence of space, some signals don't whisper, they scream. Fast radio bursts, or FRB, are among the most baffling phenomena in modern astronomy. These blasts of radio waves last just milliseconds, yet pack more energy than the sun emits in days, even weeks. They arrive without warning, flicker once and vanish, some never to repeat, others flashing sporadically like cosmic lighthouses. The first was discovered in 2007, buried in archival data from a radio telescope in Australia. Since then, hundreds more have been detected, each one a fleeting, brilliant mystery beamed across millions or even billions of light years. What could possibly produce such violent, short-lived signals? The leading suspect is magnetars, neutron stars with magnetic fields so intense they could strip the information from a credit card halfway across the Milky Way. Picture one of these ultra-dense stellar corpses undergoing a starquake, a catastrophic rearrangement of its crust, releasing a tsunami of magnetic energy as radio waves. Some repeating FRBs fit this theory neatly, their irregular bursts matching the unpredictable tantrums of these cosmic powerhouses, but not all FRBs play by the same rules. Some repeat in precise patterns like clockwork, while others explode once and go silent forever. A handful even seem to come from within our own galaxy, offering rare close-up glimpses of their behavior. Then there's FRB 2012-10, the Lorimer burst that arrived with a polarization twist, its radio waves corkscrewing through space, hinting at passage through incredibly dense magnetic fields. Every new detection adds another layer to the puzzle, another question without a clear answer. Of course, with anything this enigmatic, speculation runs wild. Could FRBs be artificial? The idea isn't as far-fetched as it sounds. A civilization advanced enough might harness pulsar-like beams for interstellar propulsion, or perhaps they're cosmic hello signals deliberately briefed to conserve energy. The truth is we don't know, and that's what makes them so thrilling. Catching these bursts is like trying to photograph lightning with a camera that takes one snapshot a day. Traditional telescopes are too slow, their fields of view too narrow, but new instruments like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, are changing the game. With no moving parts, CHIME stares at a huge swath of sky, processing data in real time to flag FRBs the instant they appear. Already, it's detected hundreds, including rare repeating bursts that let astronomers trace their origins back to distant galaxies. What's truly astonishing is what FRBs reveal about the universe itself. As these radio waves traverse the cosmos, they interact with the sparse electrons between galaxies, slowing ever so slightly. By measuring this delay, astronomers can weigh the universe's missing matter, the diffuse gas too faint to see directly. Each burst is a probe, illuminating the darkness between galaxies in ways light never could. So while we might not yet know what creates these cosmic Morse codes, one thing's certain: they're more than just curiosities. They're tools, challenges, and perhaps even messages reminding us that the universe still holds secrets waiting to be decoded, 1 millisecond burst at a time. Most stars aren't loners, they're part of cosmic couples, locked in an endless gravitational embrace. Binary star systems, where two stars orbit a shared center of gravity, are far more common than solitary suns like ours. But these stellar duos aren't just beautiful to observe, they're celestial laboratories, revealing secrets about mass, gravity, and even the afterlife of stars. Picture two dancers spinning around each other, their movements dictated by an invisible thread. The faster they whirl, the tighter that thread pulls, and the more we can learn about their hidden nature. Take eclipsing binaries, for example. These pairs line up just right from our vantage point, so one star periodically passes in front of the other, dimming its light in a predictable rhythm. By measuring how deep those dips in brightness are and how long they last, astronomers can calculate the stars' sizes, masses, and even the shapes of their orbits. It's like watching a cosmic clockwork where every tick and tock unveils another piece of data. Some binaries, like Algol in the constellation Perseus, have been studied for centuries, their eclipses so regular you could set your watch by them. But not all binary dances are so graceful. Some partners are mismatched: a massive star paired with a dense neutron star or black hole. In these extreme systems, gravity becomes a thief. The more massive object strips gas from its companion, pulling material into a swirling disk so hot it glows with X-rays. These X-ray binaries, like Cygnus X1, were among the first strong candidates for black holes, their violent interactions betraying the presence of an invisible monster. The stolen matter spirals inward, heating up to millions of degrees before vanishing past the event horizon, screaming its demise in high-energy radiation we can detect across the galaxy. Then there are the binaries that defy expectations. Some neutron stars pulse with radio waves as they orbit, their precise ticks slowing or speeding up as their companion's gravity warps space-time around them. These pulsar binaries, like the famous Hulse-Taylor binary discovered in 1974, became natural tests for Einstein's theory of general relativity. Their orbital decay matched his predictions perfectly, showing how gravitational waves carry energy away from the system, a discovery that earned a Nobel Prize and paved the way for LIGO groundbreaking detections decades later. But perhaps the most surprising revelation is how binary stars shape stellar life cycles. When a massive star in a binary goes supernova, the explosion can kick its surviving partner into a wild, high-speed journey across the galaxy. Other times, the stars merge, creating bizarre hybrid objects, blue stragglers that appear younger than they should, or even stellar vampires where one star rejuvenates itself by siphoning life from the other. And when both stars eventually die, their remnants might continue orbiting as double black holes or neutron stars, destined to collide in a final, cataclysmic embrace that shakes the fabric of space-time itself. Every binary system tells a story of birth, theft, violence, or even resurrection. By studying their intricate motions, we're not just measuring stars. We're reading the universe's diary, page by page, revelation by revelation. And with every orbit we chart, we uncover another clue about how stars live, die, and transform the cosmos around them. Galaxies have a secret. Watch any spiral galaxy spin, and you'll notice something strange. Its outer stars whip around far too quickly for the visible matter alone to hold them in orbit. According to the laws of gravity, these stars should fling off into the void like marbles from a slingshot, but they don't. Something unseen, something massive, must be anchoring them in place. This cosmic glue, this gravitational phantom, is what we call dark matter, an invisible scaffold woven through the universe, shaping everything from galaxies to the largest structures in the cosmos. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed something odd about the Coma Cluster, a group of galaxies over 300 million light-years away. The individual galaxies were moving so fast that their collective gravity, based on visible stars and gas, shouldn't have been able to hold the cluster together. Yet there it was, intact. Zwicky called the missing mass Dunkel Materie, or dark matter. At the time, few took him seriously, but decades later, Vera Rubin's meticulous observations of spiral galaxies confirmed it. Stars at the edges orbited just as fast as those near the center, defying expectations. The only explanation, a vast, unseen halo of matter, outweighing the visible stuff by a factor of 5 to 1. But how do you study something that doesn't interact with light? Astronomers have become cosmic detectives, piecing together dark matter's presence through its gravitational fingerprints. One of the most striking clues comes from gravitational lensing, the way massive objects bend light like a funhouse mirror. When Hubble images distant galaxies, some appear stretched or warped into arcs and rings. That distortion isn't caused by the visible galaxies in the foreground. It's the work of their dark matter halos curving space-time itself. By mapping these lenses, scientists have traced dark matter's distribution in stunning detail, revealing intricate cosmic webs that stretch across billions of light years. Then there's the bullet cluster, a smoking gun in the dark matter mystery. When two galaxy clusters collided, their hot gas, the bulk of their visible matter, slammed together and lagged behind while their dark matter, unfazed, sailed right through. X-ray telescopes saw the gas glowing like a cosmic traffic jam, but gravitational lensing showed the true mass had moved ahead, invisible yet undeniable. It was proof that dark matter isn't just an anomaly, it's the universe's hidden architecture, the framework upon which galaxies are built. Yet for all its influence, dark matter remains maddeningly elusive. It doesn't emit, absorb, or reflect light. It doesn't collide with ordinary matter like atoms. It's a ghost felt only through gravity. So what is it? Theorists have proposed candidates: WIMP, weakly interacting massive particles, actions, even primordial black holes, but decades of experiments, from deep underground detectors to space-based observatories, have yet to catch a definitive trace. Some detectors have seen tantalizing hints, like the annual modulation in Italy's Doma experiment, but nothing conclusive. The hunt has led to wilder ideas. Could dark matter be part of a shadow universe with its own forces and particles? Could our understanding of gravity itself be flawed, requiring a rewrite of Einstein's equations? The debate rages on, but one thing's certain: dark matter isn't just missing mass. It's the hidden hand guiding cosmic evolution, the reason galaxies exist as they do, and perhaps the key to understanding the universe's ultimate fate. Every galaxy rotation curve, every lensed quasar, every computer simulation of cosmic structure whispers the same truth: we're surrounded by a mystery, one that outmasses everything we can see. And until we solve it, the universe's shadow language remains its most profound enigma. The sun may seem like a steady, unchanging orb in our sky, but beneath its calm surface lies a raging storm of magnetic chaos. Every so often, that pent-up energy explodes outward in a solar flare, a burst of radiation so powerful it can outshine the sun's entire surface for minutes or even hours. These eruptions aren't just dazzling light shows, they're the sun's way of scribbling its secrets in fiery script, a language of plasma and magnetism that we're only beginning to decode. Picture the sun's surface as a writhing sea of plasma, crisscrossed by magnetic field lines like invisible rubber bands. When these lines twist too tightly, often near sunspots, where magnetic activity is strongest, they can snap, releasing energy equivalent to millions of hydrogen bombs in seconds. That energy accelerates particles to nearly the speed of light, heating the surrounding plasma to tens of millions of degrees. The result, a flash of X-rays and ultraviolet light that races across the solar system, followed by a slower wave of charged particles, a coronal mass ejection, or CME, that can barrel toward Earth like a cosmic tsunami. But here's where it gets fascinating. These flares aren't random. They follow patterns, clues embedded in their light that reveal the sun's inner workings. By splitting a flare's spectrum into its component wavelengths, scientists can trace the eruption's temperature, density, even the strength of the magnetic fields that spawned it. It's like reading a fingerprint left behind by the sun's fury. Some flares crackle with radio waves, their static hissing like a badly tuned radio station, while others pulse in gamma rays, the highest energy light in the universe. Each frequency tells a different part of the story. The most powerful flares, dubbed X-class, can unleash as much energy as 1 billion megatons of TNT. The infamous Carrington event of 1859, the largest solar storm on record, set telegraph wires ablaze and sparked auroras so bright they turned night into day as far south as Cuba. If a storm like that hit today, it could fry satellites, knock out power grids, and disrupt GPS systems for weeks. That's why space weather forecasting has become so critical. Flares aren't just scientific curiosities. They're existential threats to our tech-dependent civilization. Satellites like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter act as solar storm chasers, watching the sun around the clock for signs of unrest. They've spotted flares triggering shockwaves that ripple through the sun's atmosphere, or launching loops of plasma hundreds of times taller than Earth. Some flares even come with a twist, literally. Certain eruptions spiral like corkscrews, their magnetic fields kinking as they erupt, a detail that might explain why some storms hit us harder than others. Yet for all we've learned, flares still surprise us. In 2021, scientists detected a flare from Proxima Centauri, our nearest stellar neighbor, that was 100 times more powerful than anything our sun has produced. If life exists on that star's planets, it would need to weather radiation blasts we can scarcely imagine. Even our own sun has hidden tricks occasionally. Flares erupt from regions with no visible sunspots, suggesting magnetic drama unfolding deep beneath the surface. Every solar flare is a telegram, an urgent dispatch from our star's turbulent heart. And with every one we study, we're not just learning to predict space weather, we're uncovering the universal rules that govern stars across the cosmos. Because whether it's a gentle yellow sun like ours or a distant red dwarf spewing superflares, the language of stellar fury is written in the same fiery script. And we're finally learning to read it. Black holes are the universe's ultimate paradox, objects so dense they trap light itself, yet surrounded by some of the brightest phenomena in the cosmos. Take the supermassive black hole at the heart of Galaxy M87, 6.5 billion times more massive than our Sun. When the Event Horizon Telescope unveiled its image in 2019, it wasn't just a scientific milestone, it was a portrait of spacetime itself stretched to its limits. That glowing ring, the fiery halo around the shadowy abyss, wasn't just light. It was the signature of gravity bending photons into a perfect circle, a cosmic funhouse mirror reflecting the black hole's immense pull. But how does a black hole, a place where nothing escapes, become visible? The answer lies just outside the point of no return, the event horizon. As matter spirals inward, friction heats it to billions of degrees, creating a swirling disk of plasma that shines across the electromagnetic spectrum. Some particles, instead of falling in, get catapulted away in jets stretching thousands of light years, beams of energy so powerful they outshine entire galaxies. These aren't random outbursts, they're cosmic breadcrumbs revealing how black holes twist magnetic fields and accelerate particles to near light speeds. The HT's image of M87's black hole wasn't just a pretty picture. It was a precision test of Einstein's general relativity. The size and shape of that shadow matched his equations almost perfectly, confirming that even under extreme gravity, space-time warps exactly as predicted. But there's a twist. Some black holes, like the one in Galaxy M87, spin. That rotation drags space-time around with it, like honey stirred by a spoon, and the EHT team is now hunting for signs of this frame-dragging effect in future observations. A spinning black hole's shadow should look slightly squashed, a subtle distortion that could reveal how fast these cosmic monsters twirl. Then there's Sagittarius, a star, the supermassive black hole at the Milky Way's center. Though closer, it's smaller and more restless than M87's giant, its flickering light changing by the hour. Capturing its shadow required not just global coordination but patience, waiting for the rare moments when its turbulent surroundings calmed enough to snap a clear image. When the EHT finally revealed it in 2022, the result was eerily similar to M87's, suggesting that black holes, no matter their size or environment, obey the same fundamental rules. But black holes don't just warp light, they warp time. Near the event horizon, gravity slows clocks to a crawl. To an outside observer, a falling object would appear to freeze, its light reddening into invisibility as time stretches infinitely. Yet from the object's perspective, it crosses the horizon in an instant, a one-way trip into the unknown. This bizarre time dilation isn't just theoretical. It leaves traces in the flickering of surrounding matter, subtle timing glitches that telescopes can now detect. The most mysterious signal might come from black hole mergers. When two collide, they don't just send out gravitational waves, they ring like bells, their event horizons vibrating at specific frequencies. These quasi-normal modes encode the black hole's mass and spin, a cosmic fingerprint waiting to be decoded by next-generation observatories. Already, researchers have teased out hints of these tones in LIGO data, faint echoes of space-time settling into its new shape. So while black holes may be the darkest objects in the universe, they're far from silent. Their shadows sketch the shape of space-time, their jets scream across the cosmos, and their mergers send tremors through the fabric of reality. Every image, every gravitational wave, every flicker of light is a sentence in their story, one we're only beginning to translate. Because in the end, a black hole's darkness isn't an absence of information. It's a message written in the negative, a cosmic silhouette revealing where light ends and the true unknown begins. There's a moment in a star's life when it becomes the brightest thing in the universe, not for millions of years, not for centuries, but for a few glorious weeks. A supernova isn't just an explosion. It's a stellar farewell letter written in light and elements, a burst of energy so intense it can outshine entire galaxies. And within that brilliance lies the answer to one of astronomy's most profound questions. Where do the building blocks of life itself come from? Take a single teaspoon of matter from a supernova's core. Within it, you'd find atoms forged under conditions so extreme they defy imagination, temperatures exceeding 100 billion degrees, pressures that crush protons and neutrons into exotic forms. This is where the universe cooks up elements like gold, platinum, and uranium, where the iron in your blood and the calcium in your bones were first smelted in stellar furnaces. Without these explosions, the periodic table would stop at iron, leaving planets, oceans, and life itself impossible. But supernovae aren't just element factories. They're also cosmic mile markers. Type I a supernova, the thermonuclear detonations of white dwarf stars, burn with such predictable brightness that astronomers call them standard candles. By comparing how bright they appear from Earth to how bright they actually are, scientists can measure distances across the universe with astonishing precision. It was this very method that revealed the universe's expansion wasn't slowing down, it was accelerating, driven by the mysterious force we now call dark energy. Those flickering points of light didn't just illuminate dying stars, they illuminated the fate of the cosmos itself. The drama of a supernova unfolds in stages. First, the core collapses, triggering a shock wave that races outward at thousands of miles per second. For days, the star brightens as radioactive nickel, forged in the blast, decays into cobalt and then iron, pumping energy into the expanding debris. The light curve, the graph of its brightness over time, becomes a forensic tool, revealing the explosion's physics in its rise and fall. Meanwhile, the spectrum of its light splits into a rainbow of emission lines, each line a barcode identifying the elements present. Some supernova, like the famous SN 1987A, even leave behind a light echo, as their flash illuminates pre-existing dust clouds years later, like a cosmic flashbulb reflecting off interstellar fog. Yet no two supernovae are exactly alike. Some, like type Roman II, are the violent deaths of massive stars, their cores imploding into neutron stars or black holes. Others, like type Ia, are more precise white dwarfs stealing mass from companions until they cross a critical threshold and detonate like stellar time bombs. And then there are the rarities like hypernova or pair instability supernova, so powerful they obliterate their progenitors completely, leaving no remnant behind. Each type leaves a distinct signature in its light, its spectrum, and even its surroundings, like the Crab Nebula, the tangled wreckage of a supernova observed in 1054, still expanding a millennium later. Perhaps the most astonishing thing about supernova isn't their destructive power, but their creative force. The shock waves from these explosions compress nearby gas clouds, triggering the birth of new stars. The heavy elements they scatter become the raw materials for planets, moons, and someday perhaps life on worlds we've yet to discover. Every supernova is both an ending and a beginning, a death that seeds the cosmos with possibility. So the next time you look up at the night sky, remember, you're not just made of stardust, you're made of stardust that exploded. And somewhere out there, another star is preparing its own grand finale. A dazzling finale that will one day light up the sky and whisper, once again, the universe's endless cycle of endings and rebirths. Somewhere in the depths of space, a star the size of a city spins faster than a kitchen blender, beaming radio waves into the cosmos with the precision of a Swiss watch. This is a pulsar, nature's most accurate clock, a stellar corpse so dense a single teaspoon would weigh 1 billion tons on Earth. Born from the violent death of a massive star in a supernova, these spinning neutron stars don't just flicker. They pulse with a rhythm so steady, so unshakable, that they rival the best atomic clocks humanity has ever built. And their ticks aren't just cosmic curiosities, they're tools, lighthouses, even messengers from the frontiers of physics. Consider the Crab Pulsar, the heart of the supernova that lit up Earth's skies in 1054. 30 times a second, it swings its beam of radiation past our planet, like a spinning spotlight in the dark. Each pulse arrives with such predictability that astronomers once used it to test Einstein's theory of relativity, measuring how its signals slowed ever so slightly as they grazed the sun's gravitational field. But the Crab is just one of thousands. Some pulsars, called millisecond pulsars, spin hundreds of times per second, their surfaces whirling at nearly 1/4 the speed of light. These speed demons are thought to be old pulsars resurrected by stolen matter from companion stars, their rotations whipped into a frenzy like cosmic tops. Then there's the Hulse-Taylor binary, a pulsar paired with another neutron star in a deadly dance. discovered in 1974, this system became a Rosetta Stone for gravitational physics. As the two stars spiral closer, their orbital decay matches Einstein's predictions to within a fraction of a percent, proving they radiate energy as gravitational waves, a discovery that earned a Nobel Prize and paved the way for LIGO groundbreaking detections decades later. The Hulse-Taylor pulsar isn't just a timekeeper, it's a gravity lab testing the limits of our understanding under conditions no Earth experiment could ever replicate. But pulsars aren't just for physicists, they're also the universe's natural GPS. In the 1970s, NASA included pulsar maps on the Pioneer plaques and Voyager golden records, using their unique pulse patterns as cosmic address markers. The idea was simple. Any advanced civilization could triangulate Earth's position by matching these rhythms to the sky. Today, projects like the European Space Agency's Pulse mission are taking this concept further, studying how millisecond pulsars might one day guide spacecraft through the solar system, or even between stars. Their beams are so regular that timing their arrival to within a millionth of a second could pinpoint a ship's location anywhere in the galaxy. Yet pulsars still guard mysteries. Why do some suddenly change spin rates in glitches, as if their crusts momentarily crack? What creates the bizarre Black Widow pulsars that vaporize their companion stars with lethal radiation? And could their gravitational wave hum, when combined as a pulsar timing array, reveal the background chorus of supermassive black holes merging across the universe? Every pulse is a heartbeat from a stellar zombie, a beacon from a realm where matter is crushed into quantum strangeness, where gravity bends time itself. And as we listen to their rhythms, we're not just keeping cosmic time, we're decoding the universe's deepest laws, one precise tick at a time. What if everything we see, the stars, galaxies, even our own bodies, isn't truly three-dimensional, but a shimmering illusion, like a hologram projected from the edges of reality? It sounds like science fiction, but the holographic principle is a serious idea born from the deepest puzzles in physics. The story starts with black holes, those cosmic paradoxes where gravity crushes matter into oblivion. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume, as you'd expect. Instead, it's tied to the surface area of its event horizon. It's as if all the data about what fell inside is painted onto a two-dimensional boundary, like a cosmic hard drive. This odd connection between surfaces and volumes led theorists like Gerard T. Hooft and Leonard Susskind to propose something radical. Maybe the entire universe works the same way. Just as a hologram encodes a 3D image on a flat sheet, perhaps our reality is written on a distant two-dimensional surface, with every particle, every force, even time itself emerging from this underlying code. If true, it would mean the world we experience is a kind of projection, an elaborate shadow play where depth is an illusion and the true action happens at the edges. But how could this possibly work? Think of it like a movie screen. The image appears to have depth, but every detail is actually encoded in the flat pixels of the film. Similarly, the holographic principle suggests that the information needed to describe a volume of space, every star, every atom, could fit perfectly on its bounding surface, just with one Planck-length pixel per unit area. This isn't just abstract math. In 1997, Juan Maldacena discovered a concrete example, a theoretical universe where a 5D spacetime with gravity is mathematically equivalent to a 4D quantum field theory without gravity. It was the first real hint that the holographic principle might not just be metaphor, but a fundamental feature of reality. The implications are staggering. If space is holographic, then phenomena we think of as separate, like gravity and quantum mechanics, might just be different sides of the same coin. Black holes wouldn't destroy information, they'd encode it on their surfaces, preserving the universe's quantum rulebook. Even the Big Bang might be reinterpreted as a kind of cosmic rendering, with time and space emerging from a deeper, dimensionless code. Yet the most mind-bending possibility is this: if reality is a projection, then what we perceive as here might actually be processed there on some unimaginably distant boundary. It's as if every event in the universe, from a supernova explosion to the firing of a neuron in your brain, is being computed on the cosmological equivalent of a quantum hard drive trillions of light years away. The light we see, the motions we measure, might just be the readout of that calculation, flickering into existence moment by moment. Of course, proving any of this is another matter. The holographic principle remains largely theoretical, a framework that tantalizes but hasn't yet yielded testable predictions. Some scientists hope that future gravitational wave detectors might find subtle fingerprints, anomalies in spacetime's texture that hint at its pixelated underpinnings. Others are searching for echoes of the idea in quantum entanglement, where particles separated by vast distances seem to share information instantly, as if connected by some hidden surface. Whether the holographic principle holds up or not, it's already reshaped how we think about space, time, and information. It suggests that the universe isn't just speaking to us in light and motion. It might be whispering in a language of boundaries and codes, where every star, every galaxy, is part of an infinite cosmic projection. And if that's true, then the greatest mysteries of existence might not be hidden in the depths of space, but etched onto its edges, waiting to be decoded. The universe is never truly silent, not even in the deepest voids between galaxies. What looks like empty space to our eyes is actually a seething quantum ocean, where particles flicker in and out of existence so fast they defy measurement. These aren't just theoretical oddities, they're real enough to leave fingerprints on reality itself. Picture the vacuum as a cosmic trampoline, where pairs of particles and antiparticles constantly pop up, borrow energy from nothingness, then vanish before physics can catch them in the act. This quantum foam isn't just background noise. It might hold the key to one of cosmology's greatest puzzles: why the universe is expanding faster than anyone predicted. The math behind this is wild. According to quantum field theory, every point in space should contain a tiny amount of energy, a baseline hum of activity even in total emptiness. When physicists tried to calculate how much energy this zero-point vacuum field should contain, the numbers came out absurdly high, like a single cubic centimeter of space should have more energy than all the matter in the observable universe high. Clearly, something's off. Either our understanding of quantum mechanics is incomplete, or some cosmic balancing act cancels out most of this energy, leaving only a faint residue. That residue, it just happens to match the strength of dark energy, the mysterious force accelerating cosmic expansion. Here's where it gets even stranger. In 1948, Dutch physicist Hendrik Casimir predicted that these quantum fluctuations could produce measurable forces. His thought experiment was simple: place two metal plates extremely close together in a vacuum. The plates would block certain wavelengths of virtual particles from forming between them, creating a pressure imbalance. Sure enough, when scientists tested this decades later, the plates were pushed together by an invisible hand, proof that the quantum vacuum isn't just theoretical. It has real, tangible effects, now scale that up to the entire cosmos. If space itself is brimming with this latent energy, it could explain why galaxies are flying apart faster and faster. Every cubic light year of vacuum, no matter how empty it appears, might contain a tiny repulsive force that adds up across the universe's vast expanse. The catch: our best quantum calculations overshoot dark energy's observed strength by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science history. Some theorists think the answer lies in undiscovered particles or extra dimensions that cancel out most of this energy. Others propose that dark energy isn't constant but evolves over time, tied to a field called quintessence that changes as the universe expands. Then there's the radical idea that we're seeing quantum entanglement on a cosmic scale, that particles across the universe share hidden connections influencing spacetime's behavior. Whatever the explanation, one thing's clear: the vacuum isn't passive. It's an active participant in shaping reality, a quantum whisper beneath the surface of everything. And as we peel back its layers, we're not just studying empty space, we're decoding the hidden engine that might one day determine whether the universe expands forever, collapses back on itself, or tears apart at the seams. The answers won't come easy, but they're written in the static of the void, waiting for us to listen. Of all the stars in the Milky Way, none has sparked more wild theories than KIC 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who first flagged its bizarre behavior, this unassuming flicker in the constellation Cygnus does something no other star should. It dims unpredictably, sometimes by as much as 22%, in ways that defy all natural explanations. Imagine a light bulb that randomly fades for days or weeks at a time with no discernible pattern, now scaled at up to a star 1.5 times the size of our Sun, and you've got one of astronomy's greatest head-scratchers. The first clues came from NASA's Kepler Space Telescope, which monitored the star's light for years. Normally, a dip in brightness suggests a planet passing in front, a tidy, periodic blip. But Tabby's star didn't play by those rules. Its dips were irregular, asymmetrical, and far too extreme. One theory pointed to a swarm of comets, hundreds of thousands of them, eclipsing the star in chaotic waves. Another invoked interstellar dust, drifting in clumps too fine to see. But the most tantalizing and controversial idea was something straight out of science fiction: a Dyson sphere, a colossal structure built by an advanced civilization to harness the star's energy. The concept isn't entirely far-fetched. Physicist Freeman Dyson once speculated that a sufficiently advanced society might surround its star with orbiting solar collectors, capturing every photon of light. Over time, these megastructures would block starlight in unpredictable ways, just like Tabby's star. When Boyajian's team found no infrared excess, the telltale heat such structures should emit, some researchers proposed a Dyson swarm, a network of disconnected panels that wouldn't radiate as much waste heat. Others countered that even shattered comets or rogue planets could mimic these signals without invoking aliens. Then came the real curveball. In 2017, the star dimmed again, but this time telescopes caught it in action. Observations showed the fading wasn't uniform. Blue light dimmed more than red, a clue that whatever blocked the star was likely made of tiny particles like dust. That seemed to rule out solid megastructures, but the mystery only deepened. Subsequent studies found the star had been gradually darkening for over a century, a slow, inexplicable fade no known natural process could easily explain. So where does that leave us? Tabby's star has become a litmus test for how far we're willing to stretch our imaginations. Every new observation chips away at the wilder theories, yet the core puzzle remains. Some astronomers argue it's a laboratory for exotic astrophysics, perhaps a young star devouring a planet, or a magnetic anomaly we've never seen before. Others insist we shouldn't dismiss the possibility of intelligence too quickly, even if the odds are slim. After all, the universe has surprised us before. What makes Tabby's star so compelling isn't just the unanswered questions. It's the reminder that sometimes the most ordinary-looking things hide the most extraordinary secrets. Whether the answer turns out to be comets, dust, or something beyond our current understanding, this flickering enigma has already done something remarkable. It's forced us to look harder, think bigger, and wonder what else might be out there, waiting in the dark. Imagine a star so dense that a sugar cube-sized piece of it would weigh as much as Mount Everest. Now take that star and crank up its magnetic field to 1 trillion times stronger than Earth's, so powerful it could erase your credit card from halfway across the galaxy. This isn't science fiction. It's a neutron star, nature's ultimate physics lab, where matter gets stretched, squeezed, and twisted into forms we can barely comprehend. And when these cosmic monsters have especially intense magnetic fields, they earn a special name, Magnetars. One of their strangest tricks is how they manipulate light. Normally, light waves vibrate in all directions, like a jump rope being shaken randomly. But near a magnetar, those vibrations get forced into alignment by the star's monstrous magnetic field, polarizing the light into a single plane, as if the jump rope could now only swing east-west, never north-south. This polarized light carries encrypted messages about conditions so extreme that atoms themselves get stretched into needle-like shapes. Electrons spiral along magnetic field lines like cars on a cosmic roller coaster, and quantum effects we usually only see in particle accelerators play out on stellar scales. Then there are the starquakes, violent ruptures in a magnetar's crust that make our planet's earthquakes look like gentle shivers. Picture a city-sized star with a surface harder than diamond, under such unimaginable strain that it occasionally cracks, releasing energy equivalent to 100,000 suns in a millisecond. These quakes often trigger gamma-ray flares, bursts of the highest energy light in the universe, bright enough to briefly outshine every other gamma-ray source in the sky combined. In 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it ionized Earth's upper atmosphere, despite being halfway across the Milky Way. But the real magic happens when these forces combine. Some magnetars emit twisted beams of light that rotate with the star, sweeping past Earth like lighthouse beams. Others, like the famous SGR 0185, have fields so strong they actually bend the paths of X-rays leaving the star's surface, creating an effect called vacuum birefringence, where space itself becomes doubly refractive, splitting light into two polarized beams as if passing through an invisible crystal. This phenomenon, predicted by quantum electrodynamics but too faint to detect anywhere else, becomes unmistakable in the hellish neighborhood of a magnetar. What makes these stars so valuable isn't just their extremes, it's how they push our understanding of physics to the breaking point. At their surfaces, protons and neutrons may dissolve into a soup of quarks under the pressure. Their cores might harbor exotic states of matter, like superconducting fluids or hyperons, particles so unstable they vanish instantly in Earth labs. Even their magnetic fields challenge known physics. At a certain threshold, theories suggest the field should spontaneously decay, yet magnetars shrug off these limits, maintaining their monstrous magnetism for millennia. Every flicker, every flare, every polarized photon from these stars is a line in a cosmic poem, one written in the language of twisted spacetime, quantum uncertainty, and matter at its absolute limits. And as we decode their verses, we're not just learning about distant curiosities. We're uncovering the rules that govern all matter, everywhere, rules that, under normal conditions, remain forever hidden. Magnetars don't just break records, they break our assumptions, reminding us that the universe still holds laboratories where the known laws of physics are not just tested, but rewritten. The universe isn't just a random scattering of galaxies, it's an intricate tapestry, woven with threads so vast they make entire superclusters look like tiny knots. Picture the cosmos as a spider's web, with galaxies strung like dewdrops along silken filaments stretching hundreds of millions of light years. But these aren't ordinary threads. They're the backbone of reality itself, rivers of dark matter and hydrogen gas so faint we didn't even know they existed until we learned to read their ghostly signatures in the light of distant quasars. Quasars, those brilliant beacons powered by supermassive black holes, act like cosmic flashlights. As their light journeys across the universe, it passes through these filaments where clouds of hydrogen absorb specific wavelengths. The result, a barcode of missing light in the quasar's spectrum, dark lines revealing where invisible gas clouds lurk. It's like holding a flashlight behind a foggy window. The patterns in the mist suddenly become visible. By mapping thousands of quasars, astronomers have traced this hidden scaffolding, revealing a web so vast it dictates where galaxies form, cluster, and collide. The filaments themselves are more than just cosmic glue. They're highways of matter, funneling gas into dense nodes where galaxies feast and grow. Simulations show dark matter's gravity sculpting these strands first, a skeleton upon which ordinary matter slowly gathers. Over billions of years, gas cools and condenses along these threads, sparking star formation like streetlights flickering to life along a dark road. The largest filaments, like the sloshing supercluster, spanning over 1 billion light-years, even bend spacetime itself, warping the paths of light from more distant objects behind them, a phenomenon called weak gravitational lensing. Yet the cosmic web isn't static. It thrums with motion, galaxies surfing waves of dark matter in a slow-motion dance. Some regions, like the Laniakea supercluster, are rushing toward a gravitational anomaly dubbed the Great Attractor, while others stretch apart as dark energy stretches the web's threads ever thinner. And at the intersections of these filaments, galaxies collide in spectacular mergers, their violent births and deaths echoing along the web's invisible lines. What's truly astonishing is how much we've learned from absence, from the gaps in starlight, the warping of empty space, the whispers of hydrogen too diffuse to glow on its own. The cosmic web reminds us that the universe's grandest structures aren't always the brightest or loudest. Sometimes they're the quietest threads, the faintest fingerprints, the spaces between the stars where darkness itself holds the blueprint of everything. Deep in the cosmos, some lights don't just shine, they echo. Quasars, the blazing hearts of distant galaxies, are so luminous they outshine entire galaxies, powered by supermassive black holes devouring matter at staggering rates. But their brilliance isn't just a beacon, it's a cosmic stopwatch, a flickering pulse stretched and warped by the fabric of space itself. When their light passes near a massive galaxy on its way to Earth, something extraordinary happens. The galaxy's gravity bends the light like a lens, splitting it into multiple images, a phenomenon called gravitational lensing. And here's the twist, those images don't arrive all at once. Some take detours, delayed by the curvature of space-time, creating a staggered echo that reveals the universe's expansion in real time. Take the famous double quasar discovered in 1979. At first glance, it looked like two identical quasars side by side, but astronomers soon realized it was a single quasar, its light split by an intervening galaxy. The two images arrived days apart, their time delay acting as a cosmic speedometer measuring how fast the universe is stretching. Since then, dozens of these lensed quasars have been found, each with its own unique delay from weeks to years. The record holder, a quasar called SDSS J1004+4112, whose light takes over 1,400 days longer to reach us along one path than another. But lensed quasars aren't just timekeepers, they're also nature's magnifying glasses. The same gravity that bends their light also amplifies it, brightening distant objects we'd never see otherwise. In 2015, astronomers used a lensed quasar to spot a galaxy from when the universe was just 600 million years old. Its faint glow boosted 30 times by this cosmic zoom lens. Even more astonishing, some quasars get stretched into full Einstein rings, perfect circles of light, where the alignment is so precise the quasar's image wraps completely around the foreground galaxy. These rings aren't just beautiful, they're precision tools, their symmetry allowing scientists to map the distribution of dark matter in the lensing galaxy down to the tiniest scales. The real magic happens when quasars flicker. Unlike steady stars, quasars change brightness unpredictably, their turbulent accretion disks flaring and dimming. When those variations appear in one lensed image before another, the time delay between them becomes a ruler for cosmic distances. By comparing the delays to models of the lensing galaxy's mass, astronomers can calculate the Hubble constant, the rate of the universe's expansion. But there's a catch. Different lensed quasars give slightly different values, deepening the mystery of why some measurements of cosmic expansion don't quite agree. Could there be unseen physics at play, or hidden flaws in our models of dark matter? Every delayed echo, every warped image is a clue. Lensed quasars let us peer further back in time than any telescope could alone, their staggered light acting like a cosmic DVR, showing us the same event from slightly different moments. They've revealed ancient supernovae, mapped the growth of black holes across eons, and even hinted at the granularity of spacetime itself. So the next time you hear about a double quasar, remember, you're not just looking at a trick of the light. You're witnessing the universe fold time and space like origami, leaving behind whispers of its deepest secrets. Jupiter doesn't just glow with auroras, it sings. Not in sound, but in crackling radio waves, a chorus so loud it could drown out every earthly radio station combined if we could hear it. These aren't random bursts. They're the planet's magnetic field screaming under the assault of solar wind. A celestial siren song that NASA, a Juno spacecraft, has been decoding since it arrived in 2016. Picture the solar wind, a supersonic river of charged particles from the Sun, slamming into Jupiter's magnetosphere, a magnetic bubble larger than the Sun itself. The collision doesn't just spark auroras brighter than Earth's. It triggers radio emissions so powerful they pulse like a lighthouse beacon across the solar system. What makes these radio bursts extraordinary isn't just their strength, it's their structure. Unlike Earth's relatively orderly auroral radio waves, Jupiter's emissions come in two distinct flavors: decametric bursts, which pulse in rhythmic, almost musical patterns, and broadband kilometric radiation, a chaotic static hiss. The decametric waves, in particular, seem to dance to Jupiter's rotation, flaring every 9 hours and 55 minutes like clockwork, synchronized with the planet's magnetic field. Juno's close passes revealed these bursts originate from vast electric currents flowing along Jupiter's magnetic field lines, where electrons spiral into the planet's poles at nearly light speed, releasing energy as radio waves. It's as if Jupiter's magnetosphere is a colossal particle accelerator, strumming the magnetic field lines like guitar strings. But the real surprise: these radio emissions aren't just Jupiter's private performance. They're a universal language. Gas giants orbiting distant stars likely produce similar radio choruses, ones we might detect with radio telescopes like LOFAR or the upcoming Square Kilometre Array. In fact, astronomers have already caught hints of this. In 2020, a telescope in the Netherlands picked up radio signals from a star system 40 light-years away, with a pattern eerily reminiscent of Jupiter's decametric bursts. The source, a Jupiter-like exoplanet, its magnetic field presumably battering against its own stellar wind. If confirmed, it would mark the first time we've heard an exoplanet's magnetosphere, a breakthrough that could reveal which distant worlds have protective magnetic shields, a key ingredient for habitability. Jupiter's radio whispers also hold clues about its deepest mysteries. The planet's auroras, fueled by particles from its volcanic moon Io, glow even when the sun is quiet, a sign that Jupiter's magnetosphere is a self-sustaining dynamo. Juno's measurements show these auroral currents are hundreds of times stronger than Earth's, with voltages reaching 10 million volts, enough to power humanity's electricity needs thousands of times over. And sometimes when the solar wind hits just right, Jupiter's radio emissions spike into S-bursts, ultra-short signals that last mere milliseconds, like cosmic Morse code. Yet for all we've learned, Jupiter's chorus still guards secrets. Why do some radio bursts echo at frequencies that suggest they're bouncing off layers deep within the planet? Could Jupiter's core, a hypothetical mass of metallic hydrogen, be vibrating like a tuning fork, modulating these signals? And what about the faint, ultra-low frequency hum? Juno detected a sound far below the range of human hearing, possibly tied to oscillations in Jupiter's magnetic field. Every answer peels back another layer, revealing not just how Jupiter works, but how magnetic fields shape planets everywhere. So while we might never stand on Jupiter's storm-racked surface, we can still listen to it. Its radio emissions are more than noise, they're a magnetic heartbeat, a reminder that even silent giants speak in waves we're only beginning to understand. And as we tune our instruments to the cosmos, we're not just eavesdropping on one planet. We're learning the vocabulary of magnetic dialogues that might echo around countless worlds, near and far. When an exoplanet crosses the face of its star, it doesn't just dim the light, it stains it. Like holding a stained glass window up to the sun, the planet's atmosphere filters specific colors from the starlight, leaving behind a spectral fingerprint of its chemical composition. This is the magic of transit spectroscopy, and with the James Webb Space Telescope's razor-sharp vision, we're not just detecting atmospheres, we're reading their ingredient lists in astonishing detail. Take K218b, a Neptune-sized world 120 light-years away. When JWST analyzed its transit, the data revealed unmistakable dips in the starlight at wavelengths only water vapor could absorb. Not just traces, either enough water to fill oceans, steaming in an atmosphere hotter than lava. But water is just the beginning. On WASP-39b, a puffy gas giant 700 light-years distant, JWST spotted the jagged signature of carbon dioxide, the first definitive detection of this molecule in an exoplanet atmosphere. The cosmic significance, CO2 acts like a thermostat in planetary climates. Finding it elsewhere means we're not just sniffing alien air, we're learning how other worlds regulate heat, weather, and even potential habitability. Then there's the surprise methane detection on ultra-hot Jupiter WASP-80b, where temperatures should break the molecule apart. Its stubborn presence hints at unseen atmospheric dynamics, perhaps relentless winds recycling gases faster than chemistry can destroy them. The real treasure hunt, though, is for biosignatures, combinations of gases that might hint at life. Imagine oxygen and methane coexisting in an atmosphere. On Earth, that's only possible because life constantly replenishes them. Spotting that duo on a rocky exoplanet would be revolutionary, but JWST is cautious by design. It's also hunting false positives, volcanic activity, or photochemical reactions that could mimic life signals. That's why researchers get most excited by context. A little methane on a frozen world, probably geological, but paired with water vapor and weirdly skewed carbon isotopes on a temperate planet. Now that's a story worth investigating. Transits do more than reveal ingredients, they expose atmospheres in motion. During one observation of ultra-hot Jupiter WASP 76b, astronomers caught iron and magnesium bleeding into space, torn free by the star's radiation. Another world, GJ1214b, showed a flat spectrum, no absorption lines at all, suggesting a thick, hazy shroud, perhaps a global ocean of vaporized rock. Every transit is a snapshot of alien meteorology, where winds might race at thousands of miles per hour, where clouds could rain molten sapphire, and where the very air might glow with auroras fiercer than anything in our solar system. What makes JWST observations so transformative is their precision. Earlier telescopes might detect one molecule if they were lucky. JWST delivers entire chemical inventories, sometimes from a single transit. Soon it'll turn its gaze to rocky worlds in habitable zones, like those in the TRAPPIST-1 system. Will it find water vapor clinging to a temperate planet? A whiff of ozone, or something entirely unexpected, rewriting our definitions of where life could thrive. Every time a planet passes its star, it exhales secrets into the void. And for the first time in history, we're here to catch them. Somewhere in the depths of the universe, a supermassive black hole is screaming, not with sound, with gamma rays, the highest energy light in existence. These aren't random bursts, they're focused beams, narrow as laser pointers, slicing through the cosmos at near light speed. And when one happens to point directly at Earth, we witness something extraordinary. A blazar, nature's ultimate particle accelerator, flaring with energies that dwarf anything our sun could ever produce. At the heart of every blazar lies a black hole millions to billions of times more massive than our sun, feasting on surrounding gas and dust. But unlike quieter black holes, blazars are messy eaters. As matter spirals inward, some gets funneled into twin jets erupting from the black hole's poles, streams of plasma so energetic they glow across the universe. What makes blazars special is their orientation. One jet points almost directly at us, turning these cosmic flamethrowers into precision-targeted lighthouses. And when their gamma rays hit our telescopes, they carry encrypted messages about physics at the very edge of possibility. The real mystery lies in their flickering. Most cosmic objects change brightness gradually, over days or weeks. Blazars, they can double their gamma ray output in minutes, then vanish just as fast. In 2019, the blazar PKS 0226 plus 032 flared so violently it released more energy in 2 hours than our sun will over its entire 10 billion-year lifetime. These aren't just explosions, they're cosmic Morse code, hinting at processes we're only beginning to understand. Some theorists suggest the flares come from shock waves rippling through the jets, like sonic booms in a particle freeway. Others point to magnetic reconnection, a snapping and twisting of field lines that launches plasma bubbles at relativistic speeds. But the clues don't stop there. The polarization of blazar light, the direction its waves vibrate, changes during flares, suggesting the jets aren't smooth tubes but braided ropes of magnetic energy. Some blazars, like Markarian 501, even show periodic flaring, as if something in their accretion disks, perhaps a wobbling warp or a second black hole, is modulating the jet like a cosmic throttle. And then there's the enigma of their particle beams. Blazar jets somehow accelerate protons and electrons to energies 100 million times greater than anything in the Large Hadron Collider. How, we're not entirely sure, but the leading theory involves shock fronts surfing on magnetic waves, turning the jets into natural particle colliders spanning light years. What makes these gamma-ray ciphers so valuable isn't just their extremes, it's what they reveal about black holes themselves. The jet's tight focus suggests the black holes powering them must be spinning rapidly, their rotation twisting magnetic fields into a focused beam like water spiraling down a drain. Some blazars even show hints of precession, their jets slowly wobbling over years, possibly due to frame dragging effects predicted by Einstein's general relativity. And because blazars are visible across billions of light years, they act as backlights, their gamma rays interacting with intergalactic starlight to reveal the universe's hidden fog of background radiation. Yet for all their fury, blazars guard their secrets well. Why do some flare violently while others simmer quietly? What determines their flicker patterns? Are we seeing turbulence in the jet or echoes from the accretion disk? And could their ultra-high energy cosmic rays be the source of mysterious particles that occasionally rain down on Earth? Every flare is another piece of the puzzle, another line in a code we're still learning to crack. Because when a black hole screams in gamma rays, it's not just noise, it's a lecture on the most extreme physics in the universe, and we've got front row seats. For centuries, stars were little more than pinpricks of light, too distant to reveal any detail beyond their color and brightness. But modern astronomy has changed that. Today's advanced telescopes, equipped with high-resolution spectrographs, can peel back the layers of a star's surface, not by capturing direct images, but by mapping the subtle Doppler shifts in its light. Imagine a spinning ball of gas where one side is hurtling toward us, its light slightly blue-shifted, while the other side recedes, stretching the light redder. By stitching together these shifts, astronomers create Doppler maps, dynamic portraits of stars that reveal swirling storms, raging magnetic fields, and even the stellar equivalent of weather systems. Take the giant star Betelgeuse, for example. Doppler maps of its surface show colossal convection cells, bubbling pockets of hot plasma larger than our entire solar system. These aren't static features, they pulse and churn, driving the star's erratic brightness variations. In 2019, when Betelgeuse mysteriously dimmed, Doppler data revealed the culprit, a massive dust cloud ejected from one of these bubbling cells, blocking its light like a cosmic veil. Without this technique, we'd have seen only a flickering dot, not the dramatic upheaval beneath. But the real magic happens with starspots, stellar versions of sunspots, but often far more extreme. Our sun's spots come and go in an 11-year cycle, tied to its magnetic field flipping polarity. Doppler maps of other stars show similar cycles, but with wild variations. Some, like the young star AB Doradus, have spots so enormous they cover a third of the surface, distorting the star's shape into a wobbly ellipse. Others, like the rapidly spinning star Vega, reveal equatorial bands of spots racing around at hundreds of miles per second, their magnetic frenzies sparking flares that dwarf anything in our solar system. What's astonishing is how these maps expose stellar seasons. Just as Earth has hurricanes and heat waves, stars have their own climate patterns. On the Sun-like star HD 17365, Doppler shifts traced a spot migration toward the poles over years, hinting at a magnetic cycle twice as long as our Sun's. Meanwhile, the red giant mirror shows spots that flicker in and out like storm cells in a hyperactive atmosphere, their movements betraying turbulent winds rippling through its swollen outer layers. These aren't just snapshots, they're weather forecasts for alien suns, helping predict flare risks for planets orbiting them. The technique isn't limited to spots. In binary star systems, Doppler maps unravel gravitational tangos, showing how tidal forces distort stars into teardrop shapes. On pulsating variables, they capture shock waves rippling outward from the core, making the entire star breathe in and out like a cosmic bell. And in extreme cases, like the vampire star Lambda Tauri, they reveal rivers of stolen gas swirling from one star to another, a celestial heist caught in spectral fingerprints. Yet the biggest surprise might be how ordinary these phenomena are. The more stars we map, the clearer it becomes. Our sun's tantrums are mild compared to the cosmic storms raging across the galaxy. Every Doppler shift, every spot track, is a reminder that stars aren't static lanterns, they're roiling, dynamic orbs, their surfaces alive with magnetic drama. And as our maps grow sharper, we're not just charting distant suns, we're learning how every star, no matter how strange, obeys the same universal laws, just with a flair all its own. Look closely at the night sky through polarized lenses, and you'll notice something strange. The scattered starlight isn't random. It carries a faint but consistent alignment, as if the cosmos itself has brushed the light in one direction like strokes on a canvas. This isn't an optical illusion. It's the whisper of interstellar dust, trillions of microscopic grains silently shaping the galaxy around us. Each grain, smaller than a wavelength of light, acts like a celestial compass needle, aligning with the Milky Way's invisible magnetic fields. And as starlight passes through this cosmic sieve, it emerges polarized, vibrating in a preferred plane that betrays the hidden architecture of our galaxy. Dust might seem insignificant, the cosmic equivalent of cobwebs, but its alignment is anything but random. Charged particles within these grains respond to magnetic fields like iron filings near a magnet, slowly rotating until they lock into place. Over millennia, gentle interstellar winds and the subtle push of starlight nudge them into orderly rows, creating vast magnetic highways that stretch between stars. The result, a galactic fingerprint visible only in polarized light, where every photon carries a clue about the magnetic terrain it traversed. Astronomers have turned this subtle effect into a powerful tool. By mapping the polarization of starlight across the sky, projects like Planck and BICEP 2 have traced the Milky Way's magnetic skeleton in stunning detail. The patterns reveal loops and walls sculpted by supernova shocks, spiral arms twisted by galactic rotation, and even vast magnetic bubbles where star formation has blown cavities in the interstellar medium. In the Orion molecular cloud, polarized light shows magnetic fields channeling gas into dense filaments, the birthplaces of new stars. Without this invisible scaffolding, gravity alone couldn't explain how stars form with such efficiency. But the real surprise is how dynamic this dusty tapestry is. Near the galactic center, polarization measurements reveal magnetic fields tangled like spaghetti, twisted by the supermassive black hole's ferocious energy output. In contrast, the quieter outskirts show smoother, more orderly lines, a reminder that magnetism isn't just a background feature. It's an active participant in galactic evolution, shaping how gas flows, how stars ignite, and even how cosmic rays spiral across light years. The most breathtaking application might be what this dust obscures and reveals. When astronomers study the cosmic microwave background, polarized dust is usually a nuisance, masking primordial signals. But in 2014, the BICEP 2 team thought they'd spotted something revolutionary in that polarization: ripples from gravitational waves born in the Big Bang. The excitement turned to caution when follow-up studies showed galactic dust could mimic the signal. Yet even that disappointment proved illuminating. By studying dust's polarization so meticulously, we'd sharpened our tools for future discoveries. Every photon's subtle twist, every grain's quiet alignment is part of a grander story. The universe doesn't just communicate in light and motion, it encodes messages in the very dust we once thought was merely debris. And as we learn to read these polarized whispers, we're not just mapping magnetic fields, we're deciphering the silent forces that guide the birth of stars and the structure of galaxies, one aligned particle at a time. Deep in the cosmos, some celestial duos perform a deadly tango, one partner slowly consuming the other, their embrace glowing with X-rays hotter than a million suns. These are X-ray binaries, where a neutron star or black hole orbits a normal star close enough to strip away its outer layers. The stolen gas doesn't fall quietly. It spirals inward at nearly light speed, heating up until it screams in X-rays, broadcasting its agony across the universe. But these aren't random screams. They're precise, rhythmic, flickering in ways that reveal the most extreme physics imaginable. Picture a teaspoon of gas torn from a star's surface, accelerated to velocities so high that atoms shatter into plasma. As this superheated material swirls toward the black hole or neutron star, it forms an accretion disk, a cosmic whirlpool where friction raises temperatures to hundreds of millions of degrees. The innermost edge of this disk is where space itself starts to unravel. For black holes, it's the last stable orbit, the point where gravity's grip becomes inescapable. For neutron stars, it's the surface, where the plasma slams into a crust of pure neutrons harder than diamond. In both cases, the energy released is so intense it outshines entire galaxies in X-rays. What makes these systems so valuable isn't just their violence, it's their variability. The X-rays don't pulse steadily. They flicker, sometimes hundreds of times per second, in patterns that act like Morse code from the edge of spacetime. These quasi-periodic oscillations, or QPO, are thought to come from clumps of gas orbiting at specific frequencies, their rhythmic flashes tracing the fabric of warped spacetime. Some QPOs match predictions from Einstein's equations so precisely they've become laboratory tests for general relativity under conditions no Earth experiment could ever replicate. Then there are the X-ray bursts, sudden, explosive flares that erupt when too much accumulated gas ignites in a thermonuclear chain reaction. On neutron stars, these bursts can release more energy in seconds than our Sun does in a week, their light curves acting like thermometers for the star's surface. But the real fascination lies in the burst's aftermath. As the fireball cools, its fading X-rays sometimes show a strange, slow wobble, a sign that the neutron star itself is flexing under the strain, its crust vibrating like a gong struck by a cosmic mallet. Black hole binaries add another layer of mystery. Their X-rays sometimes vanish completely, as if the accretion disk has suddenly drained like a bathtub. These quiescent states may occur when the flow of gas becomes too turbulent to stay hot, collapsing into a cooler, dimmer mode. When the X-rays return, they often bring strange, high-energy tales, hints that particles are being accelerated to near light speed in the black hole's magnetic field, perhaps even forming jets that shoot outward like cosmic blowtorches. The most extreme examples push physics to its limits. In System Swift J1644+57, astronomers watched as a neutron star's magnetic field suddenly reconfigured, its X-ray output plummeting as its accretion disk was pushed back like a curtain. In V404 Cygni, a black hole's X-rays flickered so rapidly they implied its inner disk was fragmenting into chaotic clumps, each dissolving into the event horizon like drops of ink in a whirlpool. Yet for all their ferocity, X-ray binaries are more than just cosmic monsters. They're teachers. Their flickers reveal how matter behaves under gravity's worst tantrums, how magnetic fields twist plasma into submission, and how even light struggles to escape spacetime's most twisted regions. Every burst, every oscillation is a data point in humanity's grand experiment to understand the universe's most brutal environments, one searing X-ray at a time. Between the stars, where temperatures plunge hundreds of degrees below freezing and densities dip to near nothingness, an invisible alchemy unfolds. Vast molecular clouds, cosmic nurseries light years across harbor chemistry so intricate it would put any lab on Earth to shame. These frigid regions, barely warmer than absolute zero, should be chemical graveyards. Instead, they're buzzing factories where atoms link into complex molecules, from simple water ice clinging to dust grains to organic compounds like formaldehyde and even glycine, the simplest amino acid. And the way we detect them, by tuning radio telescopes to the faint whispers these molecules emit as they tumble through space, each molecular bond vibrating at a precise frequency, broadcasting its identity like a cosmic barcode. Take the Orion molecular cloud, one of the richest chemical storehouses in our galactic neighborhood. When astronomers point radio antennas toward its icy depths, they don't just find isolated atoms. They catch spectral fingerprints of ethanol, the same alcohol in your drink, alongside acetic acid, the key component of vinegar. Nearby, the Sagittarius B2 cloud harbors ethyl formate, a molecule that gives raspberries their scent. It's as if the universe is brewing interstellar cocktails, mixing ingredients that, under the right conditions, could someday spark life. But how does chemistry thrive in such harsh cold? The secret lies in dust. Microscopic silicate and carbon grains, no larger than smoke particles, act as cosmic workbenches. Atoms and simple molecules like carbon monoxide stick to their surfaces, creeping together until quantum mechanics allows them to bond. Over millennia, these frozen workshops assemble ever more complex molecules, from methanol to cyanide compounds. When a young star ignites nearby, its radiation blasts the grains, kicking the newly formed molecules into the gas phase where they spin and vibrate, emitting radio waves we can decode. The most astonishing discoveries come from hot cores, dense regions warmed by newborn stars. Here, telescopes have detected over 200 molecular species, including potential precursors to RNA. In 2020, researchers found hydroxylamine in one such core, a critical stepping stone toward amino acids. Meanwhile, the Atacama Large Millimeter Array spotted sugar molecules floating near a protostar, hinting that the universe might be prepping ingredients for metabolism before planets even form. Yet the real magic happens when these clouds collapse into planetary systems. Simulations show that complex organics survive the journey, hitching rides on comets and asteroids to seed young worlds. The Murchison meteorite, which fell to Earth in 1969, carried over 70 amino acids, many not found in terrestrial life. It's proof that space isn't just empty. It's a reservoir quietly assembling life's building blocks long before they're needed. So while these clouds may seem silent and dark, their chemistry is anything but inert. Every radio frequency chirp, every spectral line, is a syllable in a vast cosmic lexicon, one that's been writing recipes for life since the dawn of the stars. And as we decode more of these molecular messages, we're not just studying chemistry, we're reading the universe's own cookbook, page by frozen page. Every planet, moon, and asteroid in our solar system glows with hidden messages, not in words but in light. When sunlight strikes these celestial bodies, their surfaces and atmospheres don't just reflect it passively. They transform it, imprinting their chemical fingerprints onto every wavelength. A spectrometer acts like a cosmic linguist, translating these spectral hieroglyphs into stories of volcanic eruptions, ancient oceans, and even the raw ingredients of life itself. Take Jupiter's moon Europa, for example. At first glance, its icy shell appears pristine and unchanging. But when the Hubble Space Telescope analyzed sunlight reflecting off its surface, it detected a subtle dip in specific ultraviolet wavelengths, a signature that could only mean one thing: hydrogen peroxide. This wasn't just a random chemical. It was a clue, hinting at intense radiation splitting Europa's surface ice into reactive compounds, which might then mix with the hidden ocean below, potentially fueling microbial life in the darkness. Then there's Mars, where orbiters like ESA's ExoMars Trace gas orbiter scan the planet's faint atmospheric glow. By measuring how sunlight filters through thin Martian air, scientists spotted traces of methane, a gas that shouldn't linger long unless something is replenishing it. The detections come in sporadic plumes, sparking debates. Is this methane the exhaust of subsurface microbes, or the burps of geological activity? Either way, Mars's spectral whispers are rewriting our understanding of a world once thought geologically dead. Even airless bodies tell vivid stories. When NASA's Dawn spacecraft studied the asteroid Vesta, its spectrometers revealed patches of olivine, a mineral that usually forms deep inside planets. This unexpected find suggested Vesta might be a fossilized planetary embryo, a building block of the early solar system that never grew into a full-fledged world. Meanwhile, on Saturn's moon Enceladus, Cassini's instruments caught sodium salts in the plumes erupting from its icy crust, a tantalizing hint that its subsurface ocean might be leaching minerals from a rocky seafloor, much like Earth's oceans. The real magic lies in the details. Mercury's surface, baked by the sun, reflects light with a reddish tint, a spectral oddity traced to nanometer-sized iron particles scattered across its soil, the remnants of eons of solar wind bombardment. Venus's clouds, scanned by Japan's Akatsuki orbiter, absorb specific infrared frequencies, revealing swirling vortices of sulfuric acid and unknown ultraviolet absorbers that defy explanation. Every anomaly, every absorption line is a piece of a puzzle spanning billions of years, but this isn't just about the present. Planetary spectra are time machines. When astronomers compare the infrared glow of distant asteroids to meteorites in Earth's labs, they're essentially carbon dating the solar system's infancy. The Tagish Lake meteorite, for instance, matched the spectral signature of D-type asteroids, pristine relics from the outer solar system that may have delivered water and organic molecules to a young Earth. Similarly, Pluto's surface, mapped by New Horizons, shows methane ice segregated into distinct regions, a record of seasonal cycles playing out over millennia in its thin, hazy atmosphere. The grandest spectral library, though, might belong to Saturn's rings. As sunlight filters through their icy particles, it scatters in ways that reveal not just composition, but age. The rings' astonishing purity, almost entirely water ice with minimal dust, suggests they're far younger than Saturn itself, perhaps the shattered remains of a moon torn apart just 100 million years ago, when dinosaurs still roamed Earth. So the next time you see a planet gleaming in the night sky, remember, that gleam isn't just light. It's a narrative written in absorption lines and reflectance spectra, waiting for us to decode it. And with every new mission, every sharper spectrometer, we're not just exploring worlds, we're reading the solar system's autobiography, one photon at a time. Most stars orbit their galaxies in orderly loops, bound by gravity like bees to a hive, but some hypervelocity stars break free entirely, hurtling through space at speeds exceeding 1 million miles per hour, fast enough to escape their home galaxies forever. These cosmic fugitives don't just drift away quietly. They leave behind glowing contrails of ionized gas, telltale graffiti tags, marking their violent expulsion from the galactic core. The story of these runaway stars begins with a gravitational slingshot. Picture a binary star system, two stars locked in a mutual orbit, venturing too close to the supermassive black hole at the center of their galaxy. In a split second, chaos unfolds. The black hole's immense gravity rips the pair apart, capturing one star while flinging the other outward at mind-bending speeds. It's like a cosmic game of crack the whip, where the energy stolen from the black hole's rotation becomes the ejected star's ticket to freedom. The fastest of these exiles, like the star S5 HVS1 discovered in the Milky Way's outskirts, rocket away at nearly 2,000 kilometers per second. So fast they'll eventually leave the galaxy entirely, destined to drift alone through the intergalactic void. Tracking these stars is more than just celestial detective work. It's a way to weigh the invisible. By tracing their trajectories backward, astronomers can pinpoint the exact moment and location of their ejection, effectively using them as probes to measure the mass and spin of the black holes that launched them. When scientists retraced S5 HVS1 path, it led straight to Sagittarius A, our galaxy's central black hole, confirming its role as the ultimate cosmic catapult. The star's speed even hinted at Sagittarius A's spin rate, a property otherwise nearly impossible to gauge directly, but the real treasure lies in their light trails. As hypervelocity stars tear through interstellar gas, their fierce radiation ionizes the surrounding hydrogen, leaving glowing streaks in their wake like tire marks on a cosmic highway. These trails, visible in ultraviolet and radio wavelengths, reveal the density and composition of the galactic medium they traverse. Some stars, like He043 5439, exhibit bizarre chemical signatures, abnormal levels of helium and nitrogen, suggesting they were once part of tightly wound binaries where one star siphoned material from the other before their fatal black hole encounter. What makes these stellar escape artists so valuable is their rarity. Only a few dozen have been confirmed in the Milky Way, each one a time capsule preserving the conditions of its violent birth. Their trajectories are frozen memories of galactic dynamics, their compositions snapshots of stellar evolution under extreme duress. And as future telescopes like the Vera Rubin Observatory scan wider swaths of sky, they'll uncover more of these cosmic outlaws, painting a clearer picture of the chaotic forces lurking in the hearts of galaxies. So the next time you gaze at the night sky, remember, among the seemingly fixed stars, there are those racing silently toward the abyss, their light carrying echoes of a black hole's wrath and the untold stories of galactic centers too distant to see. They're not just runaway stars, they're messengers, screaming across the void in a language of speed and light, daring us to decode their origins. On August 17, 2017, the universe handed scientists a gift unlike any other, a collision so violent it shook spacetime and lit up the sky in a blaze of radioactive gold. That day, gravitational wave detectors LIGO and Virgo caught the tremors of two neutron stars merging 130 million light-years away. But this wasn't just a ripple in the cosmic fabric. Within seconds, telescopes worldwide swiveled toward the same patch of sky, capturing something never seen before, a kilonova, the fiery aftermath of the deadliest dance in the cosmos. Neutron stars are already extreme, city-sized remnants of supernova, so dense a single teaspoon weighs as much as a mountain. But when two of them spiral into each other, the result is apocalyptic. As they merge, tidal forces rip them apart, ejecting jets of superheated debris laced with neutrons at near light speed. In this neutron-rich environment, atoms don't just form, they are forged, undergoing rapid neutron capture, or the R process. It's the universe's ultimate smithy, where lighter elements are pummeled into gold, platinum, and uranium in seconds. The kilonova's glow isn't just light, It's the birth certificate of every heavy element in your jewelry, your electronics, even your body. GW 170,817, the event's official designation, was a Rosetta Stone for astrophysics. For the first time, gravitational waves and light told the same story. The gravitational signal revealed the star's masses and final moments, while the kilonova's spectrum, its rainbow of light, betrayed the presence of cesium, tellurium, and strontium, among others. But the real shock was the color shift. The explosion initially blazed blue, a sign of lighter elements, then faded to red as heavier atoms like gold took over. This chromatic evolution became a clock, revealing how quickly the R process unfolded. Then came the gamma-ray burst, a 2-second jet of energy so focused it had to be aimed almost directly at Earth to be detected. This was proof that kilonovae power short gamma-ray bursts, solving a decades-old mystery. But the most astonishing detail, the burst's delay. Gravitational waves arrived first, followed by gamma rays nearly 2 seconds later. That gap, infinitesimal yet measurable, confirmed a prediction of Einstein's relativity. Gravitational waves and light, despite both traveling at light speed, can separate slightly due to spacetime's warping near the merger. The aftermath was no less revolutionary. Radio telescopes tracked the expanding debris for months, watching as it plowed into interstellar gas, creating shock waves that glowed like cosmic embers. X-ray observatories caught hints of a structured jet, its narrow beam explaining why gamma-ray bursts are so rare to spot. Even Hubble joined in, measuring the event's distance independently, a critical cross-check that cemented neutron star mergers as cosmic yardsticks. But GW 170,817 legacy goes beyond one event. It proved that heavy elements aren't just made in supernova, as long assumed. Kilonovae might produce half the universe's gold, platinum, and uranium, scattering them into space to later seed planets and perhaps life. Every time you hold a gold ring, you're holding stardust, but not just any stardust. You're holding the ashes of a cataclysm older than dinosaurs, a collision so rare and violent that its echoes rewrite our understanding of where and how the universe builds its heaviest treasures. What makes kilonovae so extraordinary isn't just their destructive power, it's their generosity. In a single flash, they unite every tool in astronomy's toolkit: gravity, light, chemistry, and hand us a masterclass in cosmic alchemy. And with every new detection, we're not just watching stellar corpses collide. We're witnessing the moment the universe decides to sprinkle a little gold into the void. The Milky Way isn't just a majestic spiral, it's a cosmic crime scene, littered with the glittering remains of galaxies it has devoured over billions of years. These victims aren't completely gone, though. Their stars still trace ghostly arcs across the sky, stretched into rivers of light by our galaxy's relentless gravity. These are stellar streams, the shredded remnants of dwarf galaxies and star clusters, and they're rewriting the story of how our galaxy grew, not through gentle mergers, but in a series of violent collisions. One of the most famous of these cosmic scars is the Sagittarius Stream, a ribbon of stars winding around the Milky Way like a celestial serpent. This stream is all that's left of a dwarf galaxy that ventured too close. Over time, the Milky Way's gravity ripped it apart, scattering its stars into a looping trail that now spans the entire sky. By tracking the motions of these stars, astronomers have reconstructed the original galaxy's orbit, a doomed spiral that took it through the Milky Way's disk multiple times before it was finally torn to pieces. The stars aren't just debris, they're a timeline, each one a clue to when and how the destruction unfolded. But Sagittarius isn't alone. the Gaia spacecraft, mapping the positions and velocities of over 1 billion stars, has uncovered dozens of these streams, some so faint they're barely visible against the Milky Way's glow. One of the most intriguing is the Phoenix Stream, a narrow filament of stars that moves in the opposite direction of most galactic traffic. Its backward orbit suggests it came from a tiny, ancient galaxy that fell into the Milky Way long before Sagittarius, preserving a record of our galaxy's earliest conquests. What makes these streams so valuable isn't just their origins, it's what they reveal about the Milky Way's hidden structure. Like breadcrumbs leading through a forest, the stars' paths are warped by the galaxy's invisible dark matter halo. By studying how streams bend and twist, astronomers can map this elusive material in unprecedented detail, exposing clumps and gaps in the dark matter that would otherwise stay invisible. Some streams even show kinks or gaps, signs of close encounters with unseen dwarf galaxies or dark matter subhalos, like ripples from stones tossed into a pond. The most haunting streams, though, are those without a clear source. The Orphan Stream, a lonely trail of stars with no known parent galaxy, might be the last trace of a system so thoroughly destroyed that nothing else remains. Others, like the Gellum Stream, weave through the galactic halo in bizarre, contorted paths, hinting at multiple disruptive encounters over billions of years. These orphan stars are more than just debris, they are cosmic archaeology, preserving the chemical fingerprints of galaxies that vanished long before Earth formed. As telescopes grow sharper, they're uncovering even fainter streams, some barely holding together. The discovery of the Casito Stream, a wispy thread of stars on the verge of dissolving entirely, suggests the Milky Way's cannibalism isn't just ancient history, it's still happening today, with fresh streams forming as smaller galaxies are pulled apart. Every new detection adds another chapter to the story, revealing a galaxy built not just from gas and stars, but from the shattered remains of countless others. So the next time you gaze at the Milky Way, remember, those faint smudges and streaks aren't just random starlight. They're the echoes of galactic feasts, the fingerprints of a universe where even the mightiest structures grow by devouring their neighbors. And as we trace these stellar rivers, we're not just mapping the past, we're watching the Milky Way's future unfold, one stream at a time. Light doesn't just travel, it twists. Every photon that reaches us from distant stars carries more than brightness. It spins like a quantum top, its axis of rotation holding secrets we're only beginning to decipher. This isn't just physics trivia. The polarization of light, the direction its waves vibrate, could be the universe's ultimate encryption scheme, a natural language for sending messages across interstellar space without wires, without delay, and without the risk of cosmic static drowning them out. Imagine an advanced civilization encoding data not in radio waves or laser pulses, but in the quantum spin of photons themselves, turning starlight into a galactic internet. The key lies in a property called quantum entanglement. When two photons become entangled, their polarization states link instantly, no matter how far apart they are. Change one and the other changes simultaneously, a phenomenon Einstein famously dismissed as spooky action at a distance. But what if aliens harnessed this? They could transmit unbreakable codes by sending one half of an entangled photon pair to a recipient while keeping the other. Any attempt to eavesdrop would disturb the delicate quantum link, alerting both parties. Telescopes equipped with quantum detectors might one day spot these manipulated photons embedded in cosmic light, their unnatural polarization patterns standing out against the random twists of starlight like a flare in the night. We already have proof of concept technology for this. On Earth, quantum communication experiments use fiber optics to send entangled photons over hundreds of miles. China's Misha satellite even demonstrated quantum key distribution from orbit, beaming entangled photons to ground stations 1,200 kilometers apart. The challenge, scaling this to interstellar distances where photons must travel for years through dust, magnetic fields, and gravity wells that could scramble their delicate quantum states. Yet nature provides a potential solution. Some pulsars emit light with naturally high polarization, their beams so orderly they could act as cosmic reference points, helping receivers filter out noise to isolate artificial signals. The real breakthrough might come from next-generation telescopes like the Extremely Large Telescope or the proposed Quantum Telescope Initiative, which aim to detect single photons with unprecedented precision. By analyzing not just a star's brightness but the quantum states of its individual photons, astronomers could search for statistical anomalies, clusters of photons polarized in ways that defy natural processes. For instance, a sequence matching prime numbers or mathematical constants would scream artificial, especially if found in light from a star system with known exoplanets. Then there's the wilder possibility: quantum messages hidden in plain sight. The cosmic microwave background, the afterglow of the Big Bang, is already polarized in intricate patterns. What if an ancient civilization tweaked these patterns subtly, embedding information in the universe's oldest light? It sounds like science fiction, but the principle isn't far from how QR codes store data in pixel arrangements. Decoding such a message would require mapping the CMB's polarization at resolutions beyond current technology, but the payoff would be staggering proof that we're not just reading the universe's history, but someone else's deliberate annotation. Whether through entangled photons, manipulated starlight, or cosmic graffiti, the quantum spin of light offers a channel so universal, so fundamental, that any sufficiently advanced species might converge on it as the ultimate communication medium. And as our telescopes grow sharper, we're not just searching for aliens. We're learning to listen in the universe's native quantum tongue, a language where every photon could be a word, every beam a sentence, and every star a potential storyteller waiting to be heard. Black holes don't just devour matter, they spit it back out at nearly the speed of light, launching jets so powerful they pierce entire galaxies. But these relativistic jets, as they're called, hide a bizarre secret: time itself warps around them. From our vantage point, their motions appear slowed, as if the universe has hit the brakes. This isn't an illusion, it's Einstein's theory of relativity playing out in real time, with these jets acting as cosmic clocks ticking at the very edge of physical possibility. Picture a jet blasting from a supermassive black hole in a distant galaxy. The particles within it are moving at 99.9% the speed of light, so fast that time for them crawls compared to ours. A single second for the jet might stretch into hours or days from our perspective, a phenomenon called time dilation. This slowing isn't gradual, it's exponential. The closer the jet's speed gets to light speed, the more extreme the effect becomes. Astronomers have observed jets where features that should take days to move visibly instead seem to creep along over months, their apparent speed defying intuition. The most famous example, the jet from Galaxy M87, home to the first black hole ever imaged. Its towering jet, stretching thousands of light years, shows knots of material that appear to move at 7 times the speed of light, a physical impossibility. This superluminal motion is another quirk of relativity. The jet's material isn't actually breaking light speed. It's just racing toward us at such a steep angle that its light arrives in a compressed time frame, like a cosmic optical illusion. Combine that with time dilation, and you get a jet that seems to defy the laws of physics while secretly obeying them perfectly. These jets aren't just dazzling light, shows their precision tests for relativity. By measuring their apparent speeds and comparing them to models, scientists can probe the fabric of spacetime near black holes, where gravity is strongest and Einstein's equations face their toughest trials. Some jets even flicker in predictable patterns, their variations slowed by time dilation like a record playing at the wrong speed. Tracking these flickers lets astronomers map the jet's true velocities, revealing how black holes accelerate matter to such mind-bending speeds. But the real surprise is how these jets encode their own history. The farther out you look along a jet, the older its light is, creating a timeline of the black hole's activity over millennia. Younger sections still close to the black hole show extreme time dilation, while older regions appear to move normally. It's like watching a cosmic flipbook where the pages slow down near the present and speed up toward the past, a visual archive of spacetime's flexibility. Yet some jets still baffle us. A few exhibit features that change too quickly, even after accounting for relativity, hinting at processes we don't yet understand. Perhaps magnetic reconnection events or shock waves rippling through the jet. Others show bends or kinks that shouldn't stabilize at such speeds, suggesting hidden structures or external forces nudging them. Every anomaly is a clue, a piece of a puzzle that spans from the infinitesimally small quantum physics near the black hole's maw to the cosmically vast where these jets sculpt entire galaxy clusters. So the next time you see an image of a jet streaking across space, remember, you're not just looking at a beam of particles, you're witnessing time itself stretch and warp, a silent testament to the universe's most profound laws. And with every observation, we're not just studying jets, we're running experiments on the nature of reality, with black holes as our lab and relativity as the ultimate teacher. Imagine a world where trees aren't green but violet, or where oceans reflect not blue light but gold. On Earth, life paints our planet's light signature in ways we often take for granted, like the red edge, a sudden spike in near-infrared reflectance caused by chlorophyll in plants. It's a biosignature, a chemical graffiti tag left by biology on the canvas of starlight. And if life exists beyond Earth, it might leave its own distinct brushstrokes in the spectra of distant exoplanets. The key to finding it, light, not just any light, but the precise wavelengths absorbed or reflected by molecules only life could produce. The hunt for these alien light fingerprints is already underway. Future telescopes like the Habitable Worlds Observatory will scan exoplanet atmospheres for combinations of gases that shouldn't coexist without biological intervention. Take oxygen and methane. On Earth, sunlight destroys methane in decades, and oxygen reacts so readily it vanishes unless replenished. Finding both in an exoplanet's air would be like catching smoke and fire in the same room, a strong hint something's burning, or in this case, breathing. But the real jackpot would be spotting something stranger, a molecule like chlorophyllic pigments tuned to a different star's light. A planet orbiting a red dwarf, for example, might evolve photosynthesis optimized for infrared, leaving a purple edge instead of our familiar red. Then there's the possibility of artificial biosignatures, industrial pollutants like CFCs or nitrogen dioxide, which could betray the presence of technology. In 2014, astronomers modeling Earth's transit spectrum noticed something startling. Our planet's artificial lights, though faint, imprint a detectable glint in the dark. An advanced civilization might illuminate its nights with lasers or megastructures, creating unnatural spikes in their world's reflected light. Even city lights, if concentrated enough, could leave a flicker in the data, a cosmic neon sign blinking, "We're here." The challenge isn't just spotting these signals, it's distinguishing them from false positives. Geological processes can mimic life's handiwork. Volcanic eruptions spew methane, and photochemical reactions in hazy atmospheres can generate oxygen without biology. That's why scientists look for context. A little methane on a frozen world might be mundane, but paired with nitrous oxide, a gas produced almost exclusively by microbes on Earth, it starts to tell a story. The ultimate confirmation would come from seasonal variations, like the ebb and flow of plant growth altering a planet's reflectance over time, a rhythmic pulse of light echoing biology cycles. But the most tantalizing clues might come from light we can't even see. Some extremophiles on Earth fluoresce under ultraviolet radiation, a potential survival tactic against stellar flares. On an exoplanet, a sudden UV-induced glow could be a microbial scream against the cosmic dark. Meanwhile, subsurface ocean worlds like Europa might betray life through chemical imbalances in their plumes, molecules like hydrogen sulfide or methyl chloride, vented into space and detectable in infrared spectra, whispering of hidden ecosystems. The stakes couldn't be higher. A single anomalous wavelength, a flicker in the data, could rewrite history. Whether it's the red edge of an alien forest, the artificial glow of cityscapes, or the fluorescent shimmer of microbial colonies, light is the universe's oldest messenger. And as our telescopes grow sharper, we're not just searching for planets, we're learning to read their stories in photons, one wavelength at a time. The answer to "Are we alone?" might not come as a radio signal or a flying saucer, but as a subtle shift in starlight, waiting for the right instrument and the right moment to reveal it. From redshift whispers to gravitational wave echoes, the universe speaks in a symphony of light and motion. Each mystery we've explored, whether dark matter's invisible grip or the precise ticks of pulsars, adds another verse to this cosmic poem, a composition written in wavelengths and warped spacetime. Think of it like this: every flicker of starlight, every ripple in the fabric of reality, is a sentence in a story that began 13.8 billion years ago. And we're not just passive observers. With every telescope we build, every algorithm we train, we're learning to translate the universe's language, one discovery at a time. Consider how far we've come. A century ago, we didn't know galaxies existed beyond our own. Today, we're decoding the gravitational murmurs of colliding black holes and mapping the cosmic web's hidden scaffolding. The James Webb Space Telescope peers into stellar nurseries, catching light from the universe's first dawn, while LIGO listens for the faintest tremors of neutron stars spiraling into oblivion. These aren't just tools, they're extensions of our senses, amplifying whispers from the void into something we can see, measure, and understand. Yet for every mystery solved, a dozen more emerge. Why does dark energy accelerate the universe's expansion? What ignites the bizarre radio bursts from distant galaxies? Could the holographic principle rewrite our understanding of reality itself? These questions aren't just academic. They're bridges to a deeper connection with the cosmos, reminders that the universe isn't a static backdrop. It's a dynamic, evolving entity, and we're part of its unfolding narrative. The beauty of this journey lies in its shared wonder. Whether you're an amateur astronomer tracing constellations or a physicist modeling quantum foam, you're contributing to humanity's collective quest to decipher the cosmos. So the next time you step outside and look up, remember, those stars aren't just distant suns. They're characters in an epic tale, and their light carries secrets waiting to be unraveled. What fascinates you most about this cosmic story? Share your thoughts below, and if you're hungry for more deep dives into space's grand mysteries, hit subscribe. The universe has endless stories left to tell, and we're just getting started.